Okay, it's 4 p.m. so we should start our seminar. Welcome everyone to join the AOGS-RAC No.2 Atmospheric Research Working Group online seminar series number 2. My name is Xian Lin from National Central University. And since the Professor Ye cannot online today, so I'm host to this seminar. And today our speaker is Professor Andres Calabai, and from the Technical University of Madrid. And Professor Calabai is the recognized academic and accomplished professional skill in the topics of space geology, navigation, and remote sensing, and with a broad range of the analytics techniques, including the data analysis and algorithm development. Professor Calabai is currently based in Nanjing, working for the Nanjing University of Information Science and Technology, China, as an associate professor. His research interest focus on the upper atmosphere environment and the coupling between the Earth and the space weather, and the repercussions of those environments on satellites and authorizations of geodetic techniques to incorporate to the planetary variability and to test, validate, and develop geophysics models. In his earlier career, he was working as the geomagnetic engineer in Spain and the UK. Then he completed his PhD at the Shanghai Astronomical Observatory, Chinese Academy of China, Science China, and also a postdoc at the University of Colorado Boulder, USA, and he has a H index of 10 and above the 200 citation. And today's title is introduction to the upper atmosphere coupling and the advanced thermospheric mass density retrieval. And Professor Calabai, please, to your talk. Thank you.
Thank you very much, everybody, for coming today, for attending this seminar of the AOGS. I'm going to share my screen. Welcome to everybody. Thank you, and happy Professor IP inviting me for this seminar. This is the introduction to upper atmosphere coupling and advance on thermospheric mass density retrieval. This is basically done works in my PhD, and then I extended working in Nanjing, and now I'm working the same topic here in Spain in the Technical University of Madrid. I will start with the introduction and background of the topic. Then we will show the problems and challenges and the data methods. Then we will see the results, and we can have some discussion and some conclusions and plans for the future work. As you know, Earth is protected by its own magnetic field from the space, from the particles coming from the sun and the cosmic rays. And we have this magnetic field is protecting, and we have the configuration of the magnetic field here. We can see the incoming solar wind particles from high latitude. We can see the Van Allen belt, and high energy particles are in the Van Allen belts, and then all these process they have a coupling with the upper atmosphere and the magnetosphere, and you see here the magnetosphere is the shape of the magnetosphere, and the solar wind here they make the both shock, and then the particles go through the field lines because they are charged particles, and then they embed in the magnetic field. Here you can see that the complex system, and then also creating waves and diffusion and precipitation of these particles. Is very complex, the system and in the upper atmosphere, and the coupling processes are understanding all the processes is a challenge. So these variations are strongly influenced by solar and magnetospheric forcing, and then we need to measure, understand what's going on here, because we have satellites, and then we have also radio communications and all these applications that are influenced by space weather. In the high latitude, we have auroral precipitation, and then we're creating also the electric currents and changing the chemicals and the composition of the upper atmospheres. Here we can see a vertical profile of the basically some processes they happen. One side, the solar radiation is absorbed in the thermosphere here, the X-rays and the UV, and then it's creating ionization, dissociation of molecules, and then creating the ionosphere. Here we can see, for example, the space station is at about 400 kilometers here, and then going down and down. Then we have the layers of the atmosphere, and the aurora used to create here in this about 80 kilometers. So the composition of this area of the upper atmosphere here we can see in height, going from 100 to 700 kilometers. We have here the neutrals, is the higher composition, and then we have the charged particles here, including the electrons and the oxygen, nitrogen, helium. You see a higher altitude, we have lower density, and this is the particle density in cubic centimeters. Here we have the composition of the neutrals. We can see the majority with oxygen here at high latitudes, like 500 kilometers altitude, and then we have nitrogen and then the composition. Then all these components and also in general the coupling is very complex, and then we have motions from the lower atmosphere, and then also we have this coupling with energetic particles in the high latitude. We have here ionization anomaly, equatorial density anomaly, so at the same overlapping, and then we have small structures like plasma bubbles in the ionosphere, and then we have traveling atmospheric disturbances here, the aurora. So it's very complex, this and it's not well understood. Recently, these papers from 2020, 2021. So we're still trying to understand what's going on in the upper atmosphere and how can we use the models and the measurements. How can we increase the measurements to improve the models? So here we have the physics behind this upper atmosphere. Here we have the density of the atmospheric column. Then we also have electromagnetic dissipation here with the Fontaine theorem and the neutrals winds and the field aligned currents as well here. We have on the other side the thermodynamic equations, momentum equations for meridional and zonal winds, continuity equations. So it's very complex to implement all these processes in the physical models, and then to make it accurate for application. So we usually compare these models, the physical models, with measurements, or we compare with empirical models, which are more reliable to the actual state of the upper atmosphere. In terms of the chemistry, we have photoionization, collisional ionization, charge exchange. So these models are very complex. I have several inputs, and then they give us many inputs. So the physical models, we basically the scientific community programming these models with inputs like solar extreme ultraviolet. Then we have the chemistry, the boundary conditions, and then the solar, the Joule heating, and then all mixing in these equations, making conversions to obtain temperature, winds, composition, electric fields. And then we have the tides, and it's not easy to handle it. Research on upper atmosphere is for a better understanding of the space weather and within the magnetosphere, ionosphere, thermosphere system, and then for this formulation of predictive models near Earth space environment. So the major reasons to study the magnetosphere, ionosphere, thermosphere system embrace the development of models to estimate the signal propagation delay of the electromagnetic waves through the ionosphere, such as GPS or radio telecommunications. Then we have also the drag force, which is acting on low Earth orbit satellites, and is caused by the density of atmosphere, which changes with solar radiation and geomagnetic storms. Then finally, also we have the influences on technology and infrastructures, such as electric currents induced, or those in the space, like killer electrons or power outages as well, and internet outages. So these three main major applications are the ones we are dealing with. The geodetic space weather research, as we see from the geodesy, we have space geodetic observation techniques like GNS, DORIS, satellite laser range, and other applications. And then we have in this double tetra, we have the thermosphere, ionosphere, and magnetosphere is in coupling with also the solar space weather. And then we study the thermosphere through dynamic orbit determination, for example, the ionosphere through precise orbit navigations. And then magnetosphere is used for another applications, such as magnetorquers or these grids power outs, and we study for transform electric stations to prevent from power outages. Fortunately, we have artificial satellites which can provide very important measurements for these upper atmospheric conditions, from, let's say, from the ground to 20,000 kilometers, where we have this satellite, the GPS Galileo. Then we have a low Earth orbit. We have swarm arrays. They are making measurements of density and measurements of the electric state of the upper atmosphere. Here we have the ionosphere, where these satellites here. So we have previously studied many studies using these satellite swarms, arrays, CHAMP and then also we have radio occultation for the ionosphere variations and such. This one, I see, sorry. Then for measuring the thermospheric mass density, then the neutrals, we have several techniques, but not very advanced. We have such as the most accurate, they are like accelerometer-based mass density, which are accelerometers on board satellites, but are very expensive, need to calibrate, and only few missions have provided good data, such as GRACE and SWARM. Another technique is have another specific drawbacks like cost, accuracy, resolution, coverage, calibration, complexity, such as semi-major axis variation, or within the orbit determination XM, mass spectrometers, incoherent scatter radars. Then another measurements are also such ultraviolet remote sensing, which is very recent as well. And then we also want to see if we could extract this thermospheric mass density with atmospheric occultation, radio occultation. So the relevance of retrieving thermospheric mass density is very important for precise orbit determination of satellites in low Earth orbit. So the contribution of this aerodynamic drag in the position of satellite in this altitude from let's say 200 to 500 kilometers, where the satellites are orbiting mostly the Earth observation and telecommunications. In approximately 450 kilometers altitude might equal around 3 meters in one revolution along track, and it takes about 90 minutes to do one revolution. So if we move in 3 meters, one revolution is a lot. So this drag makes difficult tracking, decelerates orbits, reduces the altitude of the satellites, and shortens the lifespan of these satellites. In many applications such as remote sensing, satellite altimetry, and gravity, the orbits have to be known with an accuracy of few millimeters. And the existing models of mass density fail to provide the accuracy for this propagation of orbit because of the missing measurements input and the models which are not accurate. We have some examples here. One example with Grace accelerometer, which is in green. We can see here the error in a precise orbit determination goes from, this is about 24 hours on December 2006. We have here one geomagnetic storm, and we can see how the density sensed by the accelerometer, which is in green, and the difference with another models. Let's see, this blue one is a Dacia, which is very accurate. Then we have also the DTM. It's not here included, but we have the MCs also in red. We can see that there are very important differences between the models. That the TIGCM is a physics-based model, and you can see here that the density measured by accelerometers to the estimated by the models, they are still very, very different. And this increasing about 800% of the normal. Here on the left, we can see quiet time, and here is during the storm, and then it can increase about 800%. So I mentioned that we have raised same ghost and swarm satellites with accelerometers, but recently I have studied that we can retrieve thermospheric mass density from GPS precise orbit. So it's what we are gonna see here now. So this Cassiope satellite, or let's say Swarm Echo from NASA, is shown here in blue color. It goes from 350 kilometers to 1,300, but the thermospheric mass density can be sensed up to, let's say, 600 kilometers below the density. Above this altitude, the density is too low to be sensed, and the errors they are too noisy. So this Cassiope satellite, the Swarm Echo, has elliptical orbit. That's why it has this shape here. The other ones have circular orbits. All of them are at about between 200 to 500 kilometers altitude. So the density we obtain through this formula from Newton, we equal the force caused by this drag acceleration from the density, from the mass density, and then we compete with the drag coefficient, the cross-sectional area, then we obtain the atmospheric density due to this drag. We have here the satellite mass, and then we isolate the acceleration, and then we compare with let's say another external ancillary data. Increasing this drag increases the density. Of course, if we have higher density, we have higher drag. The method to extract the mass density, the method I started in 2015, is calculating the total acceleration from GPS precise orbit products, and we are using this ARC2 chord interpolation threshold, and then we remove the gravitational accelerations from the time varying gravity field models, and then we extract the radiation pressure accelerations from those non-gravitational accelerations to obtain the aerodynamic accelerations. Then we use the formula of Newton to estimate the mass density. This is here the errors obtained in ARC2 in the ARC2 chord interpolation here. This is basically the formula for obtaining the acceleration. And here we see that we remove from the precise orbit products, we remove the gravity the time gravity models. These models, they include the conventional model AGM 2008, the secular low degree zero tides, and for the other low degree coefficients, the seed body direct tides, the solid tides, ocean tides, and such as well as the relativity terms. Here we have approximately estimates of the magnitudes of those accelerations. We're talking about 10⁻⁸, 10⁻⁶ meters per square second. So this gravity field here the varying gravity field is computed basically from Petit and Luthum ears convections, and then we use these formulas for the geopotential, clear body, solid earth, and all. I'm applying this one in MATLAB to remove the gravitational accelerations from the total accelerations. The varying time varying Stokes coefficients up to degree 120 are computed at about 400 seconds interval, and they are calculated. The gravity for each position of the satellite is calculated using the first derivative of the gravitational potential in Cartesian coordinates. Here we replace, and then in the spherical coordinates is calculated as follows. The magnitudes, reviewing the magnitudes here again, we have the Earth gravity, fixed bodies, Earth and tide. So mean value of 8.5 here is -6, I think here. Yeah, missing here. Well, here we have the same, but in the table, we can see here it goes from -6 here to peaks -10, -12 meters square second. It's very important to take into account the transformation between reference systems because we have the sun and the moon coordinates in the International Celestial Reference Frame, and then we have to do rotations to obtain the gravity field and the tides in the International Terrestrial Reference Frame. Then we do another rotations to remove the gravity from the precise orbit. We remove the gravity, the conventional, the time varying gravity, and then we have to finally rotate to the satellite body frame. So we have here the quaternions is including the data, or in the data of the satellites. Basically, we also can obtain a long track and vertical and transversal frame, so it will be the same. Yeah. To obtain the aerodynamic acceleration, this is composed by solar radiation and the Earth albedo. So it's estimated by taking on account each plate of the satellite and then the vector normal at each plate. And then we have also for the Earth albedo, we have another parameters. We have to include this method can be saying how to make it in many papers, also my publications. Here is to compute the eclipse when the satellite crosses. Let's say the satellite is here with my hand, and then it crosses. Here is the moon or the Earth, and then it goes to umbra, penumbra, and here is the algorithm from Monterbrook and Gill to obtain the times where the coefficient to multiply these accelerations when it's in penumbra or which is in solar irradiation directly. The varying gravity field model. Also, we have to take into account the winds in the Earth north up, which, for example, it can be estimated. The horizontal winds can be estimated from, let's say, horizontal wind model, and then this one has to be rotated to the International Terrestrial Reference System to where is the velocity, and then the co-rotating atmosphere also need to be taken into account and go to the satellite body frame so we can estimate the relative velocity and the effective cross-section area. These two for the final. I guess that was a good question. I didn't understand. Well, we're gonna see here how to apply these methods into the Cassiopeia, this warm echo satellite. Here we have the pictures of the satellite. We can see here the solar panels, and then we have we can see the other materials of the surface here, and then I made also this geometric model to estimate the cross-sectional area. This one is in my paper 2020. And here is the atmospheric number density range for this satellite approximate. This is from MC's model, so we can see approximately 10 - 15 is the total of the atmospheric density lower altitudes, and then we can see this is going lower at higher altitudes. This is estimated by MC's model in some random location, some random time, so we can see approximately what is the value of this. So this is used to obtain the drag coefficient of the satellite. We can see that the satellite is Prisma, and from this Walker and Meth and Kohler paper, we can estimate through atmospheric number density the corresponding drag coefficient, which corresponds this shape of the satellite. So we can see a ratio to spherical satellite of 1.05. And then with the drag for spherical satellite, we can estimate the drag coefficient as a function of the altitude and the solar activity, with this another results from Pardini, Tobiscan, and Selmo. And finally, with these numbers, we can estimate the drag coefficient for different altitudes and for different solar flux. Here we have the drag coefficient, which once we have altitude and flux of the satellite, we just pick here the drag coefficient, which is estimated through this method. Here we have the panel properties of the satellite. We have about, I think it's 10 plates, so 1, 2, 3, about 12 plates. Here we have the area of the plate, the vector normal to the plate, the material, and then the reflectivity in the visible and in the infrared. Here for geometrical and diffusion, the coefficients have to be applied to the formulas I have shown before for the irradiative forces. The resulting accelerations from solar radiation, Earth albedo, and Earth infrared radiation are here. So for the long and the cross and the uptrack directions, and we can see it goes up to 5-8 meters square second. And here is smaller, the Earth albedo, and the infrared is even smaller than this one. Along the Cassiope orbit, we can see here the altitude goes from 150 to about, the altitude here is missing the number. Well, this is one example of the orbits. It's in real scale. Here we can see the satellite orbiting around Earth, this altitude, let's say, and here we can see that the density of the satellite is higher when it approaches to Earth. Yes, because this is a higher altitude. As you can see this map here, we can see that the lower altitudes we have higher density. Here is lower density. And this is one approach. Let's say it's one revolution when it approaches to the surf, to the lower altitudes. The density goes to 2 kilograms per square meter. This is -11, and the altitude goes from 350 is the lowest altitude here, and then it goes up, and 400-500 kilometers altitude density goes too small. So we can see in this figure the results from the Cassiope result, from the Cassiope, the swarm echo Cassiope. And in cyan we can see that it's very noisy. Then in blue we have a small solution. These variations still need to be seen if they are real variations or noisy, but we can see that is very similar to the values given by the models. We have MCs, Dacia, and we have also the HardDM, the products from Tobisca, and then we can see the comparison goes very good. Here we have the local solar time, the longitude, and the latitude of the satellite. Here is the same plot, but for several orbits. Here we see the aerodynamic drag is when approaches to when it goes the altitude goes lower, then it increases the drag because it has higher density in the drag. And then we can see during this period, which is in 20 February, was a geomagnetic storm. And then we can see here it increases the blue one, which is the Cassiope measurements. In comparison with the empirical models, MCs and Dacia, we can see that the blue one is completely showing us the magnetic storm during this period with higher accuracy than the models, more sensitive. We can see here a little more extended time series where we can see the geomagnetic storm. Here I have included the disturbance DST index, geomagnetic index, and also the emerging electric field to see that the storm just happened here at this point here. And then after we can see the variations in the Cassiope satellite in comparison to MCs, which is not reflecting these variations during the storm. Here in this panel B, the orbits, the density follows the red solid line, and then we can see these two lines, these dashed lines. They are the higher values of density, let's say in the involving boundary of this. Then we can see that it correlates with the magnetic storms. Here in this plot is more clear. In the top we have the density estimated by precise orbit determination. In the second panel we have the model MCs, and then we have in the third panel the differences between the model and the GPS measurement. We have this similar D plot, but here we have the higher value, which would correspond into the middle of this measurement. Here it starts from 400 kilometers, lower altitudes have been not included. And the boundary, the top boundary, let's say this involving is shown here in the D panel with this blue in the top of the cyan, and then we can see that it's much more realistic, the measurements done by the satellite, by GPS than this in the model. We can see here the DST and the emerging electric field also during the storm is much better represented by the measurements done by GPS, by the method. It's interesting to see that these peaks corresponds to the changes in the electric emerging field is very well correlated. The correlation goes up to 0.7 here between the satellite and the emerging field. And when we compare with the empirical model, it goes lower to 0.4. Then the same data was computed for the period between 2014 to 2020. And then we have this new thermospheric mass density data for this period. I think this next year I will compute the remaining data from 2020 to 2023 this year. And then the data has been grouped in several altitudes to see the accuracy in its range. Let's say range lower than 350 kilometers, between 350 and 400, between 400, 450, and between 450 to 500 kilometers. We have here the estimates from Casio, from the GPS, from MCs and the Dacia models. We can see very similar, but some differences between the models and the measurements at these three different ranges. In order to study the accuracy, we have some long-term statistics. Let's say this one is for the altitude between 350 to 400 kilometers. And the comparisons this is a quotient between the model and the MCs and the products from Towiska. And then we have here the quotient between the Jachia and the HasDM. We are using HasDM as a true reference, and we can see here in between Cassiope and the HasDM that has lower spread, it's not such noisy, but we have these fluctuations which are not really represented by the models. Here we have a little bit some similarities, but still have better accuracy. We can see here in the sigma, in the standard deviation. In many cases, the Cassiope has lower standard deviation than the other models. And here in the bottom panel, we have the density of the background. The comparison between the datasets of the Cassiope GPS mass density and the empirical models, Jachia and MCs, and then here we have the comparison between the empirical models. We can see that the spread of the Cassiope with Jachia is lower than with MCs, and we have even a higher correlation. Also, we can see that the has a small bias, and it can be calibrated. Then I want to finish the presentation with summarizing, saying that non-gravitational acceleration and thermospheric mass density from 2015 to 2020 can be computed from precise orbits, and the existing orbits derived from the most advanced GNSS device on low Earth orbit satellites are capable to provide the accuracy required to obtain non-gravitational accelerations with this non-numerical differentiation method. It's very important addressing the challenges related to the coupling in the magnetosphere, ionosphere, thermosphere system, and requires significant advance in geodetic observation of plasma, neutral density, compositions and velocities, observation of these energetic particles and magnetic field perturbations, both in space and ground, as well as advanced theoretical and numerical modeling capabilities. I want to introduce the joint study group we have at the GGOS. It's implemented in the International Association of Geodesy, Intercommission Committee of Theory, and is joined with the GGOS, the focus area space weather research. The commission is the Commission 4 of Position and Applications, and then we have these members. I'm the chairman of this group, and we have a very good collaboration between all the members, and you can have access to the website. I want to show you the website here.
Thanks, Professor Calabai.
No, I didn't finish.
Sorry.
Yeah, this is the website of the GGOS group. You can access just clicking, and we have these focus areas. Then you go to geodetic space weather research, where is Michael Smith, the chair of the focus area, and within this group we have the study and working groups here, and the joint study group 1 is our group, and then here I just have some information about the coupling processes between magnetosphere and thermosphere system. Then I also want to introduce the YES community, which is for Young Earth System Scientists community for early career scientists. You can join the group. It's completely free, and then announcing seminars and conferences, and there's a lot of opportunities. I'm regional representative from Southeast Asia, and I think maybe somebody today in the meeting is present from the YES community, can give some words when I finish the presentation. And also I want to invite you to submit your, I want to show you the Young Earth System. So you can go to the Young Earth System community here, the website, and then you can log in, and then we have here much information. It's very interesting. I want to introduce you this special issue. You have interesting manuscript to submit on the topic of upper atmospheric characterization for geodetic space weather research and applications. We have here the guest editors, myself, Ganglu, and Professor Olawale. We have several manuscripts at the moment. Well, we have published one, another one has been accepted, and then we have two more in revision. Welcome to submit your papers. Yeah, I think that's all. I want to introduce my own website, which you can access here and see all my publications as well. What's missing? I want a special thanks to the AOGS Regional Advisory Committee and to the AOGS Society for preparing this interesting seminar. And you are very welcome to make any questions about the topic. And here the working groups, you can access here and see we are about 1, 2, 3. I think missing here 1 or 2 members here. And then here we have the main intentions of the low latitude atmospheric research working group in the AOGS. Thank you very much. If you have any questions, I will be very happy to answer or whatever you need. Thank you very much.
Okay, and thank you, Professor Calabai. Anyone has a question to Professor? Okay, Professor, I have the question. Like when I see the Cassiope, when the Cassiope at the orbits close to like about 300 kilometers, and I see the density become very damping, right?
Where?
When the Cassiope, the orbit is close to like 300 kilometers, like 305,
yes.
And the density become very damping. And
very low, yes.
Yeah, yeah, this figure. So, and I was just curious, why is this when altitude become be like about the 300, like 350, and then the density becomes so damping.
So lower, you mean?
Yeah, I mean when the altitude becomes lower. Yeah, because when it above like 500, and I think like it's just a small, the density is just first damping very small. Yeah, but
yes, it's very small at 450 kilometers started becoming too small and higher. So let's say from 500 kilometers is to below is the most appropriate to study densities with mostly with GPS.
Yes.
And accelerometers, they can even go a little bit higher, I guess at 600 if using accelerometers because they are more accurate accelerometers, but with the GPS should be between, I think, below 500 kilometers altitude. You can see the densities go down to -11 here.
Yes.
Okay. And then if you go higher, it goes even -13, so it goes several magnitudes lower.
And and I also see some density become lower than 0, right? Is
yes, I see that. That's caused because the noisy, maybe the acceleration or some wind causing this variation.
Yeah, got it.
So, yeah. But it's very interesting that we have obtained the main variation, which is going through the orbit after removing all the gravitational accelerations, and then we can send the storms.
Yes.
During the storm is most important, so we can see the magnitude of the variations during the storm and compare with the quiet times, and then see how could affect this variation into satellite orbit.
Yes, thank you. Anyone has questions to Professor?
I have a question here. It is private, asking me what is the relationship of mass density and storm. Then we can see that I explained in the beginning that the density changes with, especially during geomagnetic storms.
Yes.
Yeah, creating here the precipitation and then creating changes in chemistry, and then increases the density in the upper atmosphere, and then increasing the drag of the satellite. So during magnetic storms, the density can increase up to even 800% of the quiet background, quite dense. You can see here, for example, that here is quite quiet, and then it goes higher here in this during the storm.
Yes. Yeah. Okay, thank you. And anyone has a question? If not, and if more question, you can maybe you can email to Professor, and we should close this seminar today. And I think like the next seminar will be November 14. Yes. And
yes, it's in the website.
Yeah,
the website of the
November 14. Yeah. And okay, and thank you everyone to join today, and thanks again, Professor Calabai, to give a wonderful talk. Thank you very much, and we should call it a day. Thank you very much, everyone. Thank you.
Thank you very much. Have a good day. Bye bye.
Bye. See you.
Thank you. Bye.